During a research experiment, it was found that the number of bacteria in a culture grew at a rate proportional to its size. At 6 a.m., there were 6,000 bacteria present in the culture. At noon, the number of bacteria grew to 6,800. How many bacteria will be there at midnight? So this problem is using exponential growth and decay modeling. And it's going to follow this pattern here. A of t equals A naught e to the kt. And A naught is going to be our initial amount of bacteria. K is the growth rate of that bacteria. In this case, I know it's a growth rate because over time, the number of bacteria is getting larger. If the amount was getting smaller, we would call it a decay rate. We have T being the time, any unit of time, but we have to be consistent throughout the problem. And A is our accrued amount. So let's try to identify what's been given to us in this problem. So it says at here, it says at 6 a.m. we have 6,000 bacteria. And then at noon, so noon is 12 p.m. we have 6,800 bacteria. So the numbers that were being given in this problem relate to a time of day and how many bacteria we have. So how many bacteria we have are A naught and A, and we have two different times. So what we could do is we could associate 6 a.m. with our beginning time. So we could say T equals 0 hours is our beginning time. And then we need to figure out what noon is. So noon would be 7, 8, 9, 10, 11, 12. That's going to be 6 hours later. And because of us using 6 a.m. as our 0 hour, we can let 6,000 be our A naught, our initial amount, our beginning amount of bacteria. And we'll let A be our ending amount, that's 6,800. So based on this and looking at our formula, we have values of time, we have values for A naught, and we have values for A. So this information is going to allow me to figure out the value of K, the growth rate of this bacteria. And once we figure out the growth rate, we'll be able to answer this question that they're asking us: how many bacteria will be there at midnight? So let's start by finding that value of K. So we start with our formula, A of t equals A naught e to the kt. We're going to substitute in 6,800. And for A of t, 6,000 for our initial amount. K is unknown, and our time is 6 hours. So to solve this, we're going to start solving by isolating the exponential. So we do that by dividing by 6,000 since this is multiplied. We're going to do that on both sides. That cancels out the 6,000 on the right. And we'll have e to the 6k. On the left, I can reduce this a bit. You know the zeros cancel because of powers of 10. They're both even, so this becomes 32 over 30, and I can go down one more time, 15 and 16, since they're both even. So now that we have isolated that exponential and reduced, we're going to be able to solve our exponential by taking the log of both sides. Take the log on the left, and the log on the right. Natural log and e are inverses of each other, so they cancel each other out, giving us 6k. And finally, I'll be able to divide 6k on both sides. That gives k equals natural log of 16 over 15 over 6. So we now have our growth rate for the bacteria. So we want to know how many bacteria will be there at midnight. So midnight's going to be at 12 a.m. So it's going to be an additional 12 hours. We don't know this number of bacteria, but we do know that's going to be 18 hours later. So I'm going to be able to use my model. A of t equals A naught, that's 6,000. E, we just figured out k, natural log of 16 over 15 over 6. And we're going to multiply that by the time. So if we want to know the amount of bacteria after 18 hours, we're going to have 6,000 e to the natural log 16 over 15 over 6 times 18. Now we're going to type this in the calculator, and when I type it in the calculator, I like to put this 18 in the front here. So I like to write 6,000 e to the 18 natural log 16 over 15 over 6. So let me get my calculator. Okay, so I have my calculator now, and we're going to type in 6,000 e the 18 natural log 16 over 15 over 6. So after 18 hours, we have 7,281, maybe we'll round to the nearest whole number, 7,282. The population of a Midwest industrial town decreased from 224,000 to 220,000 in just 3 years. Assuming that this trend continues, what will the population be after an additional 3 years? So in this example, we're using what's called population growth or decay. We have this formula, P of t equals P naught e to the kt. P naught is the initial population or starting population. K is the growth or decay rate. In this example, it will be a decay rate because our population is decreasing. We have T, and we can use any unit of time, but we want to be consistent. In this problem, it mentions a time of 3 years, so our time will be in years. And P, this P here, is the population after some period of time. So this population decreased from 224,000 to 220,000. So at the beginning, we're going to call that year 0. We have a population of 224,000, and after 3 years, we have a population of 220,000. So because we have an initial population, we can use this 224,000 as P0, our initial population, and we'll use after 3 years as our ending amount of time, and that's our P for population. So taking a look at our formula, we have values for P, P0, and time. And we're going to be able to solve for the value of K, the decay rate in this one. And then the question that's being asked here, what will the population be after an additional 3 years? So that would be at 6 years, and that's unknown at this point. So we're going to find our decay rate first, and once we find the decay rate, we'll be able to answer that question of what happened in this town after a total of 6 years. So we're going to substitute these values into our formula. We have P of t equals P naught e to the kt. P will be 220,000. P naught is 224,000. And our time is 3 years. We're going to start solving this exponential by isolating the exponential. We're going to divide both sides by 224,000. That cancels from the right-hand side, leaving us with e to the 3k. On the left-hand side, we want to reduce. We can cancel out factors of 10 by canceling out these zeros. We have 220 over 224. We can reduce that a little bit more. They're both even. So that would be 110 and 112. I think we can reduce it a little bit more. Let's see, 110 divided by 2 would be 55, and 112 divided by 2 would be 56. And we're going to solve this by taking the natural log of both sides. It's one of our techniques for exponential equations. Natural log and e are inverses of each other, so that cancels, leaving us with what's in the exponent, 3k. And we can solve for k by dividing by 3 on both sides. So we have our value of k being natural log of 55 over 56 over 3. So now we're going to be able to write out what our model is. Our model is P of t. We have an initial population of 224,000. We have our decay rate, natural log of 55 over 56 over 3 times time. And to answer this question about what happens in an additional 3 years, we're going to use a time of a total of 6 years. So this is the beginning population. 6 years later, we would have 224,000. e to the natural log of 55 over 56 times 6. Left off that 3 there. And to type this in the calculator, I'm going to write that 6 in the front. So we have 6 times natural log of 55 over 56 over 3. So let's grab our calculator. And now these are very large numbers. So you definitely don't want to do any rounding earlier in the problem with such large numbers. So we need our e in the exponent. 6 natural log of 55 over 56 over 3. And after an additional 3 years, our population has reduced even more down to 216,000. Let's round to the nearest whole number to 71. 216,071.
Thank you for checking out my videos. Have a great day.